guys, welcome back to my channel. I hope you guys are doing well. So if you are new to my channel, my name is Arnabi Mitra and I am SD at Amazon. So this video is the third video of my basic DSL lecture series, and in my previous two videos I have mainly worked on how you can find power of numbers in login time and power of numbers modulo operation, how you can do it. So if you haven't checked this video, go and quickly check those video. And this video, as you can see, we will work a program that will print all the prime factors of a given number. Now here is a catch: I have never mentioned that distinct factors. So if it would ask you to print distinct factor, you can do that as well, but it didn't ask for distinct factors, so we can take same factor again and again. Example, I know you didn't understand what I was saying. So for example, 2 is nothing by 2 square into 3, so it has 2 and 1 3. So as a result, we can return 2 comma 2 comma 3. Now if it would ask distinct factors, we would simply return 2 comma 3. So this is something I am going to explain. I guess anything distinct factor or non-distinct factor won't matter, but the thing is matter how we can do it. So in the example I have showed like what are the things we needed, and I will show you how we used to do. So basically this is a school level mathematics that we used to do whenever we used to had a very large number. For example, suppose we have 100. What we can do, we can do it like this: 2 comma 50, then 2 comma 2 comma 25, and then we can write is 2 comma 2 comma 5 comma 5. So we used to do like this, and the same approach we are going to do, but how we are going to do it, how it will help in runtime, what approach we should take, each and everything I will discuss. So let's check what are the approach there are. So as I mentioned that we are quite familiar with this school level mathematics, and we are in our code we are going to do the exact same kind of thing. So for example, we can't start with 1 because 1 is not a prime number. So the brute force approach, whenever we see the brute force approach, what you was thinking, or one can think like we can take each and every number. We can take a I from 2 to n minus 1, and we can check if that n divided by I equal modulo, like it's zero, the remainder is 0 or not. I mean n is divisible by I or not, and if it's divisible then I is prime or not. This you are thinking. Now if we are trying to do this surely going to take order of n time to iterate each and everything, and further to check I is prime or not, it's going to take some more time. So is there any shortcut or trick or something we can do so that we can at least have a confirmation that this I is not a non-prime number, or I is a prime number? Like whenever as I said in the example, when I was giving this example, at very first I make this, I take 2 because I know that 2 is the prime number, and make it 2 comma 2 into 50, and further I thought let's divide this 50. So I again take 2 and divide it like this. Now this 25 I can't divide it by 2. So I thought, can we divide it by 3? No, not 3 is possible. 4? No, for 4 is also not possible because even 2 is not giving us answer. So let's check with 5. Yeah, by dividing with 5 it's possible, so it will show like 5 comma 5. Now this 5 and this 5 both are prime, so there is no way we can move further. So similar way, what actually we do, we took our 100, divided it by 2, we got 50. So our new n, or like our new target is 50, and we can simply put this 2 to our result. Suppose we have as array, we have put here. Now again divide this 50 by 2, we got 25, we put this 2 again here. Now we try to divide it by 3, 4, not possible. We divide it by 5, yeah, that is possible. We took this 5 here, and we start with again 2, 3, 4, not possible, so divide it by 5. Put this 5 here. Now this is 1, and we can't move more than 1. Now there are some optimization we can do here, like once a number is divisible by 2, and we are at a number that is not even divisible by 2, that means after that all the things we are going to get, there is no point. I mean, this 25 is not divisible by 2, so there is very no chance that this 5 will be divisible by 2. So we can take our I as 2 initially. Later, here also our I was 2, but when that 2 got failed, we make our I 3, 3 failed, we make our I 4, 4 also failed, we make our I as 5, and this 5 is not failing. So again, at this point of time, we divide 25 with 5 and we got a 5. So should we start with again 2, 3, 4? No, because if this number would be divisible by 2, 3, 4, it would basically at first step it would get divisible. So we can start with 5 itself. So it's a kind of optimization we did here. So what we did, we have taken a number, uh, our I was initially 2, we have our condition was while our n will be greater than 1. Now if the number is divisible by I, then we will make this number n, n will be n by I, and our I will stay same, and we will continue. Else we will try I plus plus, and this is surely going to happen. Now suppose we have 13. In case 13 is itself is a prime number, and we are trying from by 2, 3, 4, 5, and this is actually not going to work, and it will go till 13, and then only like uh, it will give a result, and it will become 1. So in case of the number is a number is a prime number, if our n is a prime number, we need to run this loop for order of n times, because we have no other choice. But if our number is not prime, then we can modify, it won't run for that much time. So if we have suppose 12, how many times our loop will run? It for first two, okay, I will go to another page and show it, so that it can get clear. So for 2, at first it will divide it by 2, and it will make it 6, and this 2 will be in our result. Now 6 will again divide it by 2, and it will 3. It will try to divide it by 2, but it will try to divide it by 2, but it won't happen, so it will make I equals to 3, and this 3 is here, and it's 1. So technically in our loop we are coming 1 time, 2 time, 3 time, and actually we are coming in our loop for when I equals to 2, but it's not working, so we will go to our else part. We will come to our this else part, we will make I equal 3, and then come to our loop again, and then we will run. So we have come like around 4 times. Let's take another example. Let's take 100. So I will show with the example like how many times it's coming to the loop. First it will come to the loop, it will come to the if part, it will take 2 inside it, it will make our in as 50 and take this 2 in our result. Now in the second part again it will come to the if block, it will make our in 25 and then it will go to and take the 2 in our answer. Now third time it will come to our loop, it will go to else part and else its else part our I will become 3 and then again it for the fourth time it will come here and also else part it will come and yeah, our I will become 4. Now for the fifth time it will come to our loop and our I will now become 5. Now sixth time it will come to our loop and our I will come to the if part and it will be, it will make our n as 5. Now for the seventh time it will again come and this time our I value is already 5. So obviously it will come to the if part, it will make our n as 1. And then for the eighth time it won't come. So it's totally 7 times it's coming to the loop. Now observe one thing. If we do some log of 12, so maybe if we do a scaling operation it's coming like 4 because log of 8 is 3. Now if we do log of 100, so log of 64 is 2 to the power 6. So we can say uh, it's almost like ceiling of uh, log of 100 like uh, the, if we have 64 it's like, so it's 2 to the power 6 and it's almost like log of n time, though it's not dividing every time n to I, but it's trying like either it's dividing n to I, that I can be 2, 3, 5, all the prime numbers, or it's simply making I plus plus. So we can't say it's actually log of n, but it's almost log of n. Now the worst case possibility will be order of n, because each and every time we are doing when we have a composite number we are just simply making I plus plus. So in the worst case it may go to order of n. Now here one slight modification we can do. See, we have started with 2 and we are giving I plus plus every time. That is fine. So after 2 it will become 3. But after 3 it will become 4. Does it has any role? Like any even number other than 2 will be uh, our non-prime number. So this a slight modification we can do. After value of I is 3 we can do I instead of I plus plus we can do I plus 2. So this is one slight modification we can do, but other than that this is a log of n algorithm in average. But the if the number is a prime number it will take log order of n time. So we will check if any other way we can do. So for that why don't we just try from, as I mentioned, try from I equal the same way we are doing. Why don't we start try from I equals to 2 to something and try to find if that number is divisible by n or not, and further we can think like we are anyway discarding the composite values, like if we are dividing number by I till that number is divisible by I, like for 12 we are dividing by 2 until we are not getting a number that is divisible by 2. So why can't we do that and check for all the numbers? So what my suggestion was, like for 12, let's divide it by 2 and we will make it 6. Again divide it by 2, we will make it 3. And again, like when we have 3, try to divide this 3 we have. At the end we were doing dividing by 3. But what if we decrease this step? Or suppose for any larger number, for example 13 into 7. Suppose we have this number. So we will start from 2, then 3, then 4, 5, 6 and 7. Finally at 7 we got a divisor and we got 13. Now to get this 13 to make 1, we have to again from 7 to 8, 9, 10, 11, 12. We need to run this 6 times this loop. But this 13 is itself is an prime. So can we do some modification on it? Or to better understand, I will show you some example. Suppose we have 12. So 12 is 2 into 6, 4, 3 cross 4. By this, obviously 1 into 12 is there, but it is not required, so I am not taking this. But see, till when we have this 2, we have already got this 6. So we don't need to come till 6 to got this 2. And when we have this 3, we got this 4. So to get a divisor 4, we don't need to check it again. So I'm saying this because let me take one example where I can give you more clear details, like suppose we have a number, okay, let me take 25. See, or maybe I can take 36. So it's 2 cross 18, 3 cross 12, 4 cross 9, 6 cross 6. So if we check till this, we don't need to go and find this, because if we are doing this, we are anyway getting these numbers. So suppose at any time while checking these numbers, and obviously the prime numbers, we are checking till this numbers, we and when, like when 36 is dividing by 6, not obviously it won't get dividing divide by 6 in our approach, but once it's get dividing by 2 and followed by another 2 and then another 3. Now this 3 is left alone. For this 3 we don't need to check. As I mentioned in 13,6, we are doing this extra checks. But already we are at some point where we have got all the suppose we have pair divisions like a cross b is giving n. We are reached till this a, we have got a, we don't need to do any check for this b. So for this b, if this a is our prime number, or maybe for this 25, so we for to reach this 5 we have checked 2, 3, 4, 5. So now we have got this 5. No need to further do anything, because we it's like a pair. Or the thing I want to explain, actually if we have reached the square uh, till the square root of any number, we don't need to get more way. So suppose we have 5 70 35, and we have divided this 35 by 5 after doing I equal 2 3 4 2 3 5. Okay, and we have got this 7. Now I am saying, now again making this I equals to 5 to 7, this jump, instead of doing this jump, we can ignore it, because a 35 can have, it's like, to get the all the pairs of 35 number, we can do square root of 35, and that is less than 6, because 36 is 6, so that is less than 6. So if we have got any number that is less than 6, then there is very less chance that a greater number will be there whose pair we didn't got yet, because obviously the greater number is there, the 7 is there, but the 7's pair 5 we have already got. So if we are left with this 7, that means that this is obviously a prime number. Or suppose we have, so we can check that the prime of the square root of 18, what can it be? So it will obviously less than 5. So if we are doing this 2, we are doing this 2, and we are doing this 3, and we have reached till here, and anyway our I is 2, then this is 5. So my take is here, we can simply make our I to move from 2 to root of n, and make I equal I plus equals 2. So instead of solely depending until our n is becoming equal 1, we can have a fixed loop that will run from 2 to root of n, because by then we would get all its factors or all its pairs, and obviously all its prime pairs, because anyway the prime pairs will lie at top, like 2 is its prime pair, 3 is its prime factor, and there is no other prime factors. We will start with this 2, and we can at least this extra thing we can decrease. Similarly for a prime number, so our main focus was for prime number, how can we check this? So for 13, once we check that root of 13 will somewhat like 4, so if there is no factor till 2, then 3, and then 5, because it will become more than 4, then we can conclude that this is one prime number. Otherwise it would have at least one factor that is less than 4, because any number would have at least one factor, or if it's like a comma b fashion, then at least one number will be less than root of n. That is why I have showed you 36 or 25 was one example. uh, the it had the it's 5 cross 5, that is root of 25 is 5. It at max its first factor will be root of this number, I mean root of, anyway root of n cross root of n will give n. So it will have at least one number that is less than its square root, and this is where we find the prime numbers. So that is why basically for decreasing our chance, for in the previous algorithm everything was working fine, but for composite number it was not working fine. So that, but this algorithm is going to work fine for composite number. So what we will do, we will take for loop for n equal I equal 2, 2I is less than equal square root of n. So we just write it like this, and I plus equal we can take 2, and here we will start with I equal 3. so that it gets clear. And for 2 we can check something, like we can have another small loop until it's getting divided by 2. I can divide it by 2, and then here uh, the same thing we will do. If while n divided by I equals 0, we will make n, we will include I in our result, and our n will be, so anyway it will be one order of root n. So you may think that there is one another while loop inside this rule, but that is basically to take the same thing. I mean, if there are more 3 more 2, so that's why we are doing here. But anyway it will only decrease its number, and at any point of time uh, we this is surely going to run for order of root n, because this part is only to eliminate till that I is divided by 2, and if our I is like modified, it will increase the, it will go beyond root n, and at last obviously there will be one I left, one n left. That also, if that is not 1 or 2, we will include that as well, include that. Why we are including this n? So as I was mentioning that for 13 cross 7 we have already got 7, and this 13 is left, so this 13 also we need to include, and for this 13 we are not doing 7 8, sorry 7 9 11, this part we are not doing. So this is one square order of square root approach, and the previous one was average log of n approach. So this is a very good mathematical question, and it will clear a lot of doubt regarding prime number. So I will soon come back with another video, obviously based on mathematics, and I hope this video has cleared your doubts. If you have any query, you can let me know in the comment section, and you can also connect with me in my telegram group. You can join my LinkedIn, you can text me there. And if you like this video, please like, share, and if you haven't subscribed my channel yet, please subscribe it. Thank you. Bye.